friends, in this video we will study the time response analysis of a first order control system when the input is a unit step function, a unit ramp function and a unit impulse function. That is, for all the three input test signals we are going to find out the time response of a first order control system. So let's start with our topic. First, we will study the time response analysis when the input is unit step. First, we will see that we know that a system will be called a first order control system when the highest power of s in the denominator of the transfer function, it is equal to 1. So when highest power is 1, then that system will be called the first order control system. So if we see the transfer function of a first order control system, it will be this is the transfer function for a first order control system. You can see that the highest power of s in the denominator, it is equal to 1. Now if we draw the block diagram for it, it will be Rs is our input and Cs is the output. These are the Laplace transforms of input and the output. This is input Rs and input signal is Rt, output is Ct, Cs is the Laplace transform of it. This is our gain, or we can say that the open loop transfer function 1 upon St. The feedback will have the gain as 1. This is our error signal Et and its Laplace transform will be Es. This is plus minus. So this is the block diagram of a feedback control system, that is first order control system having unity feedback. Now in this transfer function, if we multiply this Rs in the right hand side, then Cs will be equal to Rs multiplied with 1 upon St plus 1. So this is the output response or the value of the output in terms of input. Okay, Rs was input and Cs was the output. Now if we apply different types of input on this first order control system, and if we put the value of the Laplace transform of those input test signals, then we can get the output response. Output response we will get in terms of Laplace transform Cs. If we take its inverse Laplace transform, then we will be able to get Ct, which is the output response. So here we are going to take different types of input test signals like unit step function, unit ramp and unit impulse function, and for those input test signals we are going to find out the output response. So first we will take when the input is a unit step function. So when input is unit step function, Rt, which is our input signal, it is equal to 1. And if we take its Laplace transform, then it will be equal to 1 by S. So we are going to put the value of this Laplace transform Rs in this equation and we will get Cs. So Cs will be equal to 1 by S into 1 upon St plus 1. We have put the value of Rs in this. Now we are going to take the partial fractions of this term 1 upon St plus 1 so that we can apply the inverse Laplace transforms formulae on it. So partial fraction will be a by s plus b upon st plus 1. This is how we get the partial fractions. So let's find out the value of a and b. If we take the LCM, it will be st plus 1, and it will be a multiplied with st plus 1 plus bs. So multiply this a here, ast plus a plus bs, and the denominator terms are same, so we can cancel them and we will equate it to 1. Now if we see the left and the right hand side of this equation, the constant term on the right hand side is a. So a will be equal to 1 because constant term on left hand side is 1. Now here the coefficient of s are at plus b, and on the left hand side the coefficient of s is not present, so it will be equal to 0. A we have already calculated, it is 1. So put the value of A here. So B will be equal to minus of T. So we have got the value of A and B. So we can get the partial fractions of this CS. Just put the value of A as 1 and B as minus T here. So CS will be equal to A is 1, so 1 by S minus T upon S T plus 1. Now take T common from the denominator. This will be S plus 1 by T. T and T will be cancelled here. So we are left with CS equal to 1 by S minus 1 upon S plus 1 by T. Now we can take the inverse Laplace transform of this CS so that we can get CT. CT will be equals to 1 by S, so its inverse Laplace transform will be 1. It is for unit step function, minus we have 1 upon S plus 1 by T, so it is e raised to the power minus 1 by T into T, or we can say that CT is equals to 1 minus e raised to the power minus small t upon capital T. So this is the equation of the output response when the input is a unit step function. Now we are going to calculate the error signal ET, and error signal is the difference of the input signal and the output signal. Input signal is the unit step function, so it is 1 minus CT we have calculated 1 minus e raised to the power t upon t. So we have put the value of CT here. Now 1 minus 1 it is 0, and minus minus it will be plus. So error signal will come out to be e raised to the power minus t by t. Now if we calculate the steady state error, so steady state error is limits t tends to infinity et. So we are going to apply these limits t tends to infinity on this error signal. So when we apply the limits, its value will be 0 because e raised to the power infinity it is 0. So steady state error for the unit step function first order control system, it is coming out to be 0. Now output response we have obtained is 1 minus e raised to the power minus t by t. So if we plot this output response with respect to time, then it will be 1 minus this exponential term. Okay, so the output response plot will be like this is 1 and 1 minus this is 1 minus e raised to the power minus t by t, and this is e raised to the power minus t by t. So this green line which is showing upwards, it is our output response Ct, and this decaying exponential e raised to the power minus t by t, it is our error signal Et. Okay, and this green dashed line, it is 1 unit because we have 1 minus e raised to the power minus t by t, and on the x-axis we have time. If we see this value will come out to be 0.98, and this time is called the transient time. And after 0.98, this time is called the steady state response of the system till infinity. So this is the output response of a first order control system when the input is a unit step input. Now here we have this term capital T. So what is this capital T? This is called the time constant. And this time constant, it is related to the speed of the system. That is how fast the speed of response of system is. If the value of t is small, the response will be fast. And if the value of t is large, then the response of the system will be slow, or we can say that the response of the system is sluggish. So this is how the time response, this time constant, it shows that how quickly the response of the system is, how fast is the response of the system, and how quickly the system is reaching to its steady state value. Okay. Now, in this graph of the output with respect to time, we have seen that the output, it increases exponentially. This is 1 minus e raised to the power minus t by t. So it is increasing exponentially. So if we find out the slope at any point, then that slope will be equal to dc by dt at t equals to 0. So we are going to differentiate the output equation. Output equation is 1 minus e raised to the power minus t by t. So its differentiation will be 1 upon t e raised to the power minus t by t, and we have to calculate the slope at t equals to 0. So dc by dt at t equals to 0, we will put the value. This is 0 because t we have to put 0, so it will come out to be 1 by t. So slope at time t equals to 0, it is equal to 1 upon the time constant. So we can say that when the output response of the system, it has reached to 63.2% of its final value, it is equal to 1 time constant. And if it has reached to 86.4% of its final value, then it is equal to 2 time constant. And if it has reached to 98%, then it is equal to 4 time constants. That is 4t. And this 4t is called the settling time of the system. So you can see that this time constant, it is playing a very important role in finding out that how fast the system is reaching to its steady state value or its final value. If it has reached to 63.2% of its final value, so that will be equal to 1 time constant. If it has reached to 86.4%, then it is equal to 2 time constant. And if it has reached to 98% of its final value, then it is equal to 4 time constant, and that time required will be called the settling time of the system. So this was the output response equation when the input is a unit step function. We have calculated the error in this case, that is ET, and it was coming out to be minus T by T. And steady state error also we have calculated, limits T tends to infinity, e raised to the power minus T by T, and it is equal to 0. Okay. Now we will consider the second case when our input to the first order control system, it is a unit ramp function. Okay. So second case we will take. So when input is unit ramp function, we know that for unit ramp, the input signal is t. This is the unit ramp function. So if we take its Laplace transform Rs, it is equal to 1 upon s square. Okay. So we have written Cs equals to Rs into 1 upon s t plus 1. So here we are going to put the value of Rs. So Cs will be equal to 1 upon s square st plus 1. Okay. Now we are going to get the partial fractions of this. So partial fraction of Cs will be. So this is the output response. We have get here this Cs. So now we are going to write the partial fractions of this. So Cs will be equal to. So this is, we have written by the partial fraction method, that 1 upon s square st plus 1, its fractions can be written as a by s plus b upon s square plus c upon st plus 1. Now we can get the value of a, b and c. We will equate this. If we take the LCM, then its LCM will be s square st plus 1. So we will multiply this with a s st plus 1, then b st plus 1 plus c s square. Now denominators are same, so we are going to equate the numerator parts. Here we will have a s square t plus as plus bst plus b plus cs square equals to 1. This is 1 we have written. Now the coefficient of s square is c plus at, and coefficient of s square on the right hand side, it is s square is not present, so we have 0. Coefficient is 0. S coefficient on the left hand side is a plus bt, and on right hand side no coefficient is present, so we will equate it to 0. Constant term we have is b here, so b will be equals to 1. Now putting the value of B in this equation, we will get the value of A. So A will be equals to minus T. And if we put the value of A here, this is equal to A plus T equals to 0. So A equals to minus T. And if we put here, then C will be equals to minus T into T plus C equals to 0. So C is equals to T square. So we have got the value of B, A and T. We are going to put these values in this and we will get the partial fractions of CS. So CS is equal to A was minus T by S, B was 1 upon S square and C was T square. Now next step will be to get the inverse Laplace transform of this. So inverse Laplace transform of CS is CT minus T by S. 1 by S, its inverse Laplace transform is 1. It is a unit step function. So it will be minus of T. 1 upon S square, its inverse Laplace transform will be plus T. And plus T square upon ST plus 1. So we will write here plus T e raised to the power minus T by T. Okay. How we are getting this? We have applied the inverse Laplace transform formulas directly. This is for 1 by S, it is 1. Then 1 by S square, it is T. And this is, if we take T common from it, then it will be S plus 1 by T. So it will be e raised to the power minus T by T and 1 T will be cancelled out. So we will get this as the output response. If we rearrange the terms, we are getting T minus T plus T e raised to the power minus T by T. So this is the output response of a first order control system when the input is a unit ramp function. Now next step will be to calculate the error signal. So error signal is RT minus CT. RT is the input signal which is T for unit ramp and CT we have already calculated here. So if we open the bracket, it will be T minus T, that can be cancelled, minus minus plus T and minus plus minus T e raised to the power minus T by T. So this is the error signal, ET. If we want to calculate the steady state error, then we will apply the limits t tends to infinity on this error signal. So steady state error is given by so if t tends to infinity, then this term will be 0 and only capital T is left. So steady state error is equal to time constant for the unit ramp function. And this steady state error, it is called the positional error. It is called positional error because the output, it is lagging behind the input. If we draw the output response was T minus capital T plus T e raised to the power minus T by T. So T was our input, okay. This was our input, which is RT equals to T, the unit ramp function, and it is with respect to time. So output will be lagging behind it. Okay, output will be this, that is t minus capital T plus t e raised to the power minus t by t, and this is our lagging time. And it is coming out to be t, also known as the steady state error. So the output, it is lagging behind the input, that is why this error is called the positional error. So this was the response when our input is a unit ramp function. Next we will consider the third input test signal, that is unit impulse function. So let's see that what will be the output response in this case. So for unit impulse function, it is represented by RT equals to del T. It is unit impulse function having the value infinity at time t equals to 0, and at all other points its value is 0. So its Laplace transform will be 1, and we are going to put this value in this equation from where we have started. So here we are going to put Rs equals to 1. So Cs will be equal to So our third case will be when the input is unit impulse function. So for unit impulse function, the input RT, it is equal to del T. And if we take its Laplace transform, then Rs will be equal to 1. So we have the transfer function Cs equals to Rs into 1 upon St plus 1. This is what we have started, that Cs upon Rs is equals to 1 upon St plus 1. Rs we have shifted to the right hand side. So here we are going to put the value of Rs here. So Cs equals to 1 upon St plus 1. Now if we take T common, then it will be 1 upon T, and we are left with S plus 1 upon T. So this can be written as 1 by T upon S plus 1 by T. Now if we take the inverse Laplace transform, we will get this is for e raised to the power minus 80. So we can write the inverse Laplace transform of Cs will be Ct. So Ct will come out to be 1 by T e raised to the power minus T by T. This 1 by T is written as it is, and this S plus this is A, so it is e raised to the power minus 80. Apply the standard inverse Laplace formulas, so it will be e raised to the power minus T by capital T. Again here T is the time constant, so if we plot this output response with respect to time, it will be an exponential. This is 1 by T, and we have the exponential here. So this is 1 by T e raised to the power minus T by T, and this is the output response with respect to time. So we have studied the output response of first order control system for unit step, unit ramp, and unit impulse function. Let's form the table here. These are the three input test signals for which we have find out the output response of first order control system. Unit ramp, it is 1 by s square. Unit step is 1 by s and unit impulse is 1. So its output response was coming out to be for unit step the output response was, and for unit impulse now if we analyze or if we see the output response for these three input test signals, we will see that unit step it is the derivative of unit ramp and unit impulse it is the derivative of unit step signal. Okay, so unit step it is the derivative of unit ramp and unit impulse it is derivative of unit step. Now if we see their output responses, we can see that this output response of unit step it is the derivative of unit ramp. If we take the derivative with respect to t, then it will be 1. This will be 0 because it's a constant term, and its derivative will be 1 upon t. So this t and t will be cancelled and minus sign will come outside and it will be as it is e raised to the power minus t by t. And if we take its derivative, then 1 will be 0. Again minus 1 by t, so minus minus will become plus 1 by t and this term is as it is. So this output response of unit impulse it is the derivative of the output response of unit step. So if we remember the unit ramp output response, then we can find out the output response for unit step and unit impulse by taking its derivative. Okay. So this is how we can remember the output responses for all the three input test signals in case of a first order control system. So in this video, we studied the time response analysis of first order control systems for all the three types of signals. So I hope that this topic is clear to you. Thank you.